So, we will do quantum Hall effect in graphene, and this will be a derivation of the Landau levels, and after that we will just talk about the conductivity without explicitly calculating them, but then you know that conductivity can be calculated using Kubo formula. There is one small thing that is important in this context is that see, the plateaus come when there is a flux that is threaded through the system, and that flux has to match with the flux quantum, and the flux quantum has a value which we have denoted several times by this. This has a value some 2 into 10 to the power minus 15 Weber. So, this flux one has to match for an external field to thread through the graphene or the honeycomb lattice. Now, this honeycomb lattice has this sides, or the lattice constant is like 2.46 angstrom, and if one does a back of the envelope calculation, the area of this unit cell, which is just a honeycomb structure, is like root over 3 by 2 a square, and this comes out to be something like 0.05 nanometer square, 0.051 nanometer square. So, if I have to multiply a magnetic field with this area in order to find the flux, then that magnetic field has to be few kiloteslas or even more, and that is a very large magnetic field. So, that is why graphene, if you have to see quantum Hall effect in graphene, the magnetic field has to be very large, larger than what we have seen for the 2D electron gas or the gallium arsenide structures that we have talked about earlier. All right. We will ignore this part for the moment and pretend that everything is similar to the quantum Hall effect in a 2D electron gas. That is, the momentum, the mechanical momentum gets renormalized by this vector potential, and it happens here as well, excepting that we now have a lattice structure, and not only the lattice structure, there is 2 atoms per basis. So, it is a matrix equation that we have to solve, and we will go ahead and solve that matrix equation and find the energy corresponding to the Schrodinger equation, which we will call as a Landau levels. Just to remind you that the Landau levels for a 2D electron gas has a form which was n plus half h cross omega, where omega is EB over m, and that is the cyclotron frequency which depends on the magnetic field. We will see here how Landau levels, they depend on both n, the quantum number, relevant quantum number, and b, the magnetic field. All right. So, we will use a gauge similar to earlier. So, we will use a Landau gauge. That means your A equal to minus by x cap. We could take the other Landau gauge as well, that is bx y cap. It will give rise to same result. And just to remind you that the Hamiltonian in this particular case is of the form, it is a Vf and a sigma dot p. I have absorbed the h cross here, or we could write it as h cross Vf into sigma dot k, where p is the momentum or k is the wave vector. And this Hamiltonian, in presence of a field, transforms into it becomes h cross Vf sigma dot p minus Ea. This is the standard prescription, which we call as Peierls coupling, and this is how the momentum transforms and so on. So, we will write down explicitly this equation, and right now we are doing it for a given k, that is a Dirac point, but however we will generalize it to 2 Dirac points, like writing the Hamiltonian in a unified manner for both the Dirac points, but that we will do later. Let us carry on with this calculation for the moment. So, the matrix equation becomes equal to Vf into, we will write down the, so this is your sigma x and px minus E Ax, because this is So, we have taken it as Ax equal to minus By and plus, so this is your sigma, and then we have a sigma y I 0 and a Py. There is no change in Py because the gauge is purely in the x direction. The two component wave function psi a and psi b. So, this is equal to psi a and psi b. Okay. So, remember that sigma does not denote the spin degrees of freedom, it denotes the sublattice degrees of freedom, which are nothing but the A and B sublattices. So, this 2 by 2 structure is purely because of the sublattice structure, which we call as pseudo spinor, and it does not have anything to do with the actual spin or the real spin of the electrons. Okay. So, let us call this as equation 1. Let us write down the two equations. Because this is a 2 by 2 equation, we can explicitly write them opening up in terms of psi a and psi b. So, this is Vf and Px minus Ipy plus Eby, and this is psi a psi b, this is equal to E psi a. So, the psi b is related to psi a and vice versa. So, Vf is equal to Px plus Ipy plus Eby. Well, we can write only one bracket here. So, this is equal to psi a equal to E psi p. Okay. So, this is equation number 2. Let us call them as 2a and 2b maybe. So, this is 2a and this is 2b. Okay. These two equations, just we get it from equation 1, and if you eliminate one of them in favor of the other, say we eliminate psi a and solve for psi b, then what one gets is that. So, basically from 2b or 2a you calculate psi a and put it back into 2b, that is exactly what is done. So, this is equal to Px minus Ipy, this is just algebra that I am doing here. So, it is Eby and Px plus Ipy plus Eby and psi a, this is equal to E square psi a. So, this is just psi b is being eliminated, or we could have done the other way around. So, here of course, we put 2b into 2a, not 2a into 2b. So, let us write it that eliminating psi b. Okay. And you keep simplifying it. So, this becomes equal to Px square plus Eby square plus I Px plus there is a commutator there. So, Eby and which is a commutator with a Py. This is just from the two signs that we get here, and then a Py square, and this is a commutator bracket. So, let me change this bracket to another one. So, put a big first bracket here, and psi a, this is equal to E square by Vf square psi a. Just to remind you, Vf is the Fermi velocity of electrons in graphene. And then simplifying further, so it will be Px square plus Eby square minus EH cross B plus Py square. We simply use the commutation relations. Px of course commutes with Py, but Py does not commute with y, and Ypy we use as IH cross. So, once we do that, so we get, so this is psi a is equal to E square by Vf square psi a. Let us call this as equation 3. So, this is the equation which gives you psi a, or rather the Schrodinger equation for psi a. So, one has to remember that Px does not commute with x, or and so on. So, the wave function for this, or the solution of this, would be like a psi a would be some you know, f of y, which is some function of y. So this is a free particle motion in the x direction, because there is no x in this inside the Hamiltonian term, that is this term here, there is no x, but there is a y. So it is a free particle in the x direction, and like a harmonic oscillator in the y direction, okay, y, because Py will not commute with y. So this is simply equal to, the wave function is ikxx. Of course, there is a complicated normalization constant which we are not writing, but there it is there, okay. So if we substitute, so this is the solution. I hope you understand where the solution comes from. This was discussed in details when we did the 2D electron gas problem, the same problem in 2D electron gas, and then so this is some function of y which we do not know, and then there is a propagating part or a plane wave part which is in the x direction, okay. So what we do is that we substitute 4 into 3. And what one gets is the following. So one gets as px plus eby square. Again, a little bit of algebra, but these are required in order to arrive at the final result. We have solved for the wave function, or rather made an ansatz of the wave function, unnormalized wave function, but we still are far from knowing the eigenvalue of the problem, and both are required. The eigen function will tell you what the electronic wave functions are corresponding to the Landau levels, and the Landau level, their dependence on the quantum number as well as B have to be found out as well, okay. So it is Eh cross B plus a Py square. So along with me, you should verify all these things. If I have missed a factor or something, you should correct it. Vf square, and this is equal to f of y exponential ikxx. So this is substituting that. This replace px as minus ih cross del x. Here there is one small point that needs a mention, that even though we are doing it on a lattice, we are substituting this momentum operator as minus ih cross del x, which is known of course, but if you remember, your del x or ddx is nothing but f of x plus h, say for example minus f of x divided by h limit h tends to 0. This is the definition of the derivative, the first derivative, or you can also write it as limit h tends to 0 f of x plus h minus f of x minus h divided by 2h. That is also a central difference formula, or the direct formula, which is mostly used in mathematics. Both are acceptable. And how we go from a continuum version to a lattice version is what I am showing here. So if you replace px by minus ih cross del x, it becomes equal to minus ih cross del x, not del x, plus eby square f of y exponential ikxx minus ebh cross f of y exponential ikxx minus h cross square del 2 f y del y2 exponential ikxx, and this is equal to e square by vf square f of y exponential ikxx. So this is the Schrodinger equation, and we can operate this del x on these function f of y exponential ikx, and that will give me a kx term and so on. And similarly, the del 2, of course, fy del y2, there is no dependence. So this del y2 will be acting only on the f of y. So if you do a bit of simplification, then what comes is that h cross kx plus EBY square and of f of y exponential I kxx minus EH cross B f of y exponential I kxx minus h cross square del 2 f del y2. This f is a function of y and exponential I kxx, and this is equal to e square by vf square f of y exponential I kxx. Okay. Of course, the exponential term etc. that cancels out from both sides because they are not equal to 0. So, further simplifying. So, let me see the equation number. So, let us call this as equation number 5. So, if we simplify, then this becomes equal to h cross square and then a kx plus EBY square minus EB over h cross minus del 2 del y2, and so this f of y equal to e square by vf square f of y. Okay. So, this is the same as Schrodinger equation that we started with. It is in a much simplified form here. So, this will be like del 2 f of y del y2 plus EB over h cross square h cross kx divided by EB plus y square f of y minus EB by h cross f of y equal to h cross e square divided by h cross square vf square f of y. Okay. So, this is the further simplified form, and finally, we can also write it as minus just changing the sign there del 2 plus EB by h cross square y minus y0 square f of y minus EB by h cross f of y equal to e square by h cross square vf square f of y. Okay. Where y0 is called as a guiding center, we have seen this, or the magnetic length, so to say. Let us call this as equation 6. All right. Your y0, so let me write down y0. So, y0 equal to minus h cross kx over EB. Okay. So, this is that y0, and using this we have del 2 f of y del y2 plus e square divided by h cross square vf square plus EB over h cross, this is f of y minus EB over h cross square y tilde square. I will tell you what y tilde is, and f of y equal to 0, where y tilde is equal to y minus y0. Okay, which we have written. So, this is only for simplicity. So, we introduce this. Then finally, in terms of this, this equation, the above equation is written as del 2 f of y del y2. So, we get a second order differential equation, linear differential equation in y. So, this is of course, it is not a linear equation because there is a y square involved. Okay. So, second order differential equation, right. So, this is EB over h cross and e square divided by h cross square vf square and h cross over EB. Just bear with me for some time, this is only algebra that I am doing in order to simplify things, and so there is a plus 1 minus EB by h cross y tilde square and f of y equal to 0. So, we get a differential equation f of y, and the solution will give us the eigen functions that we have made an ansatz about. So, let us take again introduce another variable So, introduce say alpha square equal to EB over H cross such that this is written as del 2 f of y del y 2 plus alpha square E square by H cross square V f square and H cross over EB plus 1 minus alpha square y tilde square and f of y equal to 0. So, inside the square bracket let us introduce another one, another variable which is equal to beta equal to E square divided by H cross square V f square, and this is actually divided by alpha square. So, this alpha square should go down, which I forgot to write it there, and alpha square and plus 1, let us call that as beta. So, this quantity is equal to beta. So, we have 1 over alpha square del 2 f y del y 2 and plus beta minus alpha square y tilde square and f of y equal to 0. Okay. So, what equation number would this be? 6. So, let us call it as 7. So, now we have to solve for f of y. Okay. If you introduce a new variable, which is equal to say q equal to eta y tilde, where eta is some scaling, then we get this as del 2 f of y del q 2 plus beta minus q square f of y equal to 0. You have to now refer to this to Bransden and Joachim for the chapter on simple harmonic oscillator. There you had got the similar looking equation called as the Weber's equation, and from here the quantization of the energy levels come, and this energy level quantization comes as beta equal to 2n plus 1. So, C Bransden and Joachim so, what is done is that in order to solve this Weber's equation, you have to assume a power series solution, and when you put a power series solution inside at all values of y, that is at small y and large y, you want to have a solution which is a polynomial times a Gaussian type of function, it is exponential minus say y square by 2 and things like that, but that is not possible until or unless you assume that there is the polynomial would get truncated. It is not an infinite series, because an infinite polynomial series would become an exponential again, and when it becomes an exponential again, it sort of defeats the purpose, because the exponential along with the Gaussian actually makes it a diverging exponential function, which is not allowed, but this is the only solution to the problem where you actually truncate the polynomial up till a given number of terms, so that it does not blow up and become a, or rather it does not become an exponential function, and this is given in Bransden and Joachim, and see the chapter on simple harmonic oscillator. So, beta becomes equal to 2n plus 1, that tells you that your E square divided by H cross square V f square eta square becomes equal to plus 1, becomes equal to 2n plus 1. So, the eigenvalue, so 1 will get cancelled from both sides, this one will come here. So, this E becomes equal to E plus minus becomes equal to plus minus H cross V f or omega b, which is E b over m and a root over n. That is the structure of the Landau level. Okay. And the unnormalized wave functions we have already talked about, but let me do a little bit more on that. So, instead of the equidistant Landau levels that we have obtained for the 2D electron gas, that is n plus half h cross omega, where n equal to 0, 1, 2, etc. Here the Landau levels do not depend on the index n in a linear fashion, rather it depends on it in a quadratic fashion. Okay. So, omega b is actually root over 2 EB over h cross. Okay. We can actually write it as let me not write it as omega b. Of course, it depends on b, but omega b actually has been used for the cyclotron frequency. So, we will write it as omega tilde, okay, which is this. All right. So, now what is the structure of the wave function? The wave function is f of q, which is equal to some a n exponential minus q square by 2, and then there is a Hermite polynomial in q, and Hermite polynomial has a property that when n is even, it only comprises of even powers of q, that is q to the power 0, q square, q4, q6, etc. And when n is odd, it is an odd function of q, that is it contains odd powers of q like q, q cube, q to the power 5 and so on. So, as you change q to minus q, this odd term changes sign while the even term remains same. So, one can find actually the normalization by using this the total wave function to be, so this is like minus infinity to plus infinity psi square equal to dy equal to 1, and this will give you there is a little lengthy calculation, but it is done several places. So, this is equal to eta divided by 2 n factorial root over pi whole to the power half. Okay. So, that is the normalized wave function because it depends on this n. Okay. So, this is, and then you can put it and then get these are the Landau levels and so on, and the Landau level wave function, let me write it the full wave function. This is only the y part or the q part, because q and y are related, which we have said. This is equal to, so psi n x y, this is given by some EB over h cross whole to the power 1/4 1 by 2 to the power n n factorial this to the power half, and then we of course have this exponential functions which is freely moving in the x direction, and then we have these exponential EB over h cross y minus y0 square, and then the Hermite polynomials, which is nothing but root over EB by h cross and y minus y0. So, in this gauge the wave function is the particle actually propagates like a free particle in the x direction, whereas it executes a simple harmonic motion in the y direction about some y0, which is given by the expression that we have talked about earlier. So, this energy of course does not depend upon the quantum number corresponding to kx, and that is why it is degenerate. So, any quantum number kx, so kx is also like quantized like 2 pi over Lx into n, where n is the corresponding quantum number, let us call it as m. So, this is true for any value of m, and that is why it is degenerate, and practically the degeneracy could be infinitely large. Okay. So, this is the main answer is, or rather the inference of this problem is here, where we have found the Landau levels to have this particular form. Okay. Let me show the structure of the Landau levels here. So, this is the structure of the Landau levels. This is because it is a square root dependence. Now, you see that instead of the Landau levels depending, rather they are equidistant, they are, this case in graphene they are not equidistant, they in fact are, as you go larger and larger n values, you get lower and lower differences between the Landau levels. And not only that, there are these all the values above n equal to 0 and all the values below n equal to 0 are equally probable. That is, they can take positive and negative values, which was unlike the case of a 2D electron gas. Okay. So, this is the structure of the Landau levels. They are not equidistant. The maximum is here. Okay. So, this is the maximum distance between the Landau level, and because of these n equal to 0 and n equal to 1 Landau levels, or n equal to -1, here both positive and negative integers are allowed. So, the maximum difference comes here, and these sort of differences are so large that there is one can see actually Landau levels at room temperature or even larger than that. Okay. Let me show you how the Landau levels depend on B. If you see this expression that I have shown you here, there is a omega tilde which depends upon root over B. So, this actually depends on these Landau levels, actually depend upon like root over n and B, something like that. Okay. So, it's square root of B as well as square root of n. I am leaving out other factors at the moment, but it is like root over n and B, and which is what you see here. You see that E as a function of B has this structure. There is a central n equal to 0 level, and these are 1, 2, 3, 4, 5, 6 above n equal to 0, that is 0 energy, and these are the values below 0, n equal to 0. And this is B in Tesla. As I said earlier, that you need much larger values of the magnetic field in order to see quantum Hall effect in graphene. So, it is swept till about 400 Tesla. Okay. So, once we have gotten the Landau levels and the wave functions, etc., one can easily use the Kubo formula that we have talked about, that we have described, how to calculate conductivity. So, using that one can calculate the conductivity, and finding the conductivity, one would know that how does the conductivity depend upon this n. Okay. It was sigma xy equal to ne square over h for a 2D gas, whereas this may not be equal to ne square by h, and this difference in the behavior of both the Landau levels between the 2D electron gas and graphene arises from the fact that we are talking about chiral massless fermions, relativistic fermions in this case, which are of course, as we said several times earlier, that they are not really relativistic. The scale is set by the velocity scale is set by the Fermi energy instead of the speed of light, but still the dispersion is linear. So, this linear dispersion along with the massless behavior of the chiral fermions. What do I mean by chiral fermions is that if the fermion sort of goes around one of the Dirac points in a clockwise direction, it will go anti-clockwise in the other Dirac point, about the other Dirac point at E equal to 0. Okay. So, before we go to talk about the quantum Hall plateaus or how the quantization looks like, it is probably instructive and I will go through it quickly. However, I sort of suggest that you should look at these derivation quite carefully and maybe sort of get used to it. These are matrix equations that we are solving, and then we are of course converting them into a set of equations, and this set of equations are being solved self consistently. Now, what I will do is that this is the situation at one k point, and you need to actually talk about the two k points, the two Dirac points or the two valleys together in order to do this, to understand in a more detailed fashion the structure of the Landau levels and the wave functions contributing to the n equal to 0 Landau level. See here, very importantly, because the difference between the n equal to 0 and n equal to 1 is very large, as I have shown, mostly the n equal to 0 Landau level is mostly talked about, or even in experiments one sees the lowest Landau level. So, I extend this and in a sketchy manner talk about both the k and k prime points. So, we do an analysis with both k and k prime points together, unified description. Then we will write down the Hamiltonian for both k and k prime as so this is like Vf. Now, it will not be a 2 by 2, but it will be a 4 by 4, 2 coming from the sublattice degrees of freedom, that is A and B, and multiplied by another 2 coming from the 2 valleys. In addition, if you really want to talk about the spin degrees of freedom, then you will have 2 more degrees of, or rather this size of the matrix goes up by another factor of 2, which means it becomes 8 by 8, but that is not required as long as the spin orbit coupling can be ignored. And in graphene, fortunately or unfortunately, the spin orbit coupling is quite weak. So, this is a 0 and a px plus ipy and a 0 0. This is a minus px plus ipy 0 0 0, and this is like a 0 0 0 px minus ipy and a 0 0 px plus ipy 0 and so on. Okay. So, this is the wave function, or rather this is the Hamiltonian that one has to solve, and by solving again one gets these Landau levels, which you have already got. So, we have done it for only one k point. Now, I want to demonstrate, as I said, that I will not do a very detailed calculation like the one that I have done earlier. I will only sketch the salient steps so that you can fill it in. So, we have this psi, which will be, let us write it as a component like a psi a k prime, a psi b k prime, and a psi a k and a psi b k. Okay. So, that is the 4 by 4 structure, one because of this k, that is the valley degree of freedom, and the other would be the sublattice degrees of freedom. So, if we write down this, so this E into psi a k is equal to V f p x minus I p y psi b k and E psi b k is equal to V f p x plus I p y and a psi a k and so on and so forth. Okay. So, everything that we have done. So, we again substitute solving these equations. So, E square just exactly similarly that we have done earlier, it is k, it is equal to h cross square V f square p x minus I p y p x plus I p y and a psi a k. Now, remember these p x and p y, they include the these vector potentials, which we have not written here, but they would eventually include this. So, just simplifying it. So, E square psi b k is equal to h cross square V f square p x plus I p y p x minus I p y and a psi b k. So, now we get 2 equations, and these 2 equations can be solved, and you have while you solve there will be. So, what we do is that we change p x to p x plus E b y. I am just using a different gauge, same as Landau gauge, but here we are changing the p x to p x plus E b y. So, again of course, in the last thing also we have taken the gauge in the x direction. So, that is the Landau gauge, and then once you do that and do some bit of simplification, what one gets is the following. It is h cross square V f square psi b k equal to p x plus E b y square plus E H cross B plus P y square, and this is equal to psi B k and so on. Okay. These k and k are the Dirac points. I should write it with a vector, but I forgot writing it here. So, please put a vector everywhere. Okay. So, we arrive at again this E square by H cross square V f square minus E H cross B psi B k equal to P x square, say let us call it as tilde, plus P y square tilde plus psi B, this is psi B and k and so on. So, where your P x tilde square equal to P x plus E b y square and so on, and of course, your P y tilde, just to have a symmetry we have written it as P y tilde, both as with tilde, but this is what. So, I am doing exactly the same calculation now, combining both of them, both the k and the k prime points. So, it is E square by H cross square V f square minus E H cross B psi B k equal to P x square plus P y square by 2 m psi B k equal to half, let us call it a k tilde y minus y 0 square plus P y square by 2 m psi B k and so on. Okay. As where your k tilde equal to nothing but E square B square by m and y 0 equal to P x over E b, okay, or H cross k x over E b. All right. So, we are doing a similar analysis and so on, and then here what we get is a 1 over m E square divided by H cross square V f square equal to 2 n plus half H cross omega b plus H cross omega b, which gives you a 2 n H cross omega b by m. So, n is equal to 0, 1, 2 etc. and so on, and then of course, what we get is this is equal to sine of n root over of n, and that is why we wrote it earlier with mod of n, and this is equal to a V f and 2 H cross E b square root divided by m. Okay. So, this is the thing, and you can write it as H cross omega tilde sine of n, this is what we have written, and a mod of n. Okay. So, this is the Landau levels and so on, and then there are a few comments that can be made here. So, basically the lowest Landau level is of course n equal to 0, and this lowest Landau level is somewhat special, and because it receives contribution from only one sublattice, say the A sublattice for the Dirac point at k, and from the other sublattice, that is B sublattice at the other Dirac point, that is k prime, whereas all the other Landau levels, that is n not equal to 0 Landau levels, they receive contributions from both the sublattices, and that is why the n equal to 0 is actually special here, whereas in the 2D electron gas there is nothing special about any of the Landau levels. Okay. So, let me write the wave functions at the k and k prime points. So, it is psi n k and k, this is at a k point. So, this is equal to some a n divided by some root over L exponential minus I k x. So, let us call it as a L x, and now then you have a 0 0 sine of n minus I, and this is a sine n minus 1 k, and it's psi n k. So, just from the one sublattice here, for the other one it is equal to k and k prime, this is equal to some a n by root over Lx exponential minus I k x x, and again you have a psi n k s g n n minus I psi n minus 1 k and a 0 0. That is the structure of that, and these a n is equal to 1 for n equal to 0, and this is equal to 1 by root 2 for n not equal to 0. Okay. So, these are these things, and just to make sure the definition of this. So, SGN of n equal to 0 for n equal to 0, and it is actually the sign. So, n by mod n for n not equal to 0. Okay. And each of these psi's, well, we are using the same psi. So, let me write it as a big psi here. So, the small psi's are n k are these exponential minus, which are the Gaussians, it is y minus y 0 square divided by L b square, and the h n y minus y 0 divided by L b. That is the Hermite polynomial. Okay. So, these are the Landau levels and their structures for this graphene. We have done an extensive study. We first done it for one k point, any of the k points rather. We have not distinguished the Hamiltonian, we have simply taken it as Vf sigma dot k, but there is a sign that you know at one k point with respect to the other. So, if you take that into account, the k and k prime as well as the a and b becomes a 4 by 4 problem, slightly more complicated, but you can still solve it. And now we will not go and do calculation using the Kubo formula, but I will tell you the results that comes. So, it is integer quantum Hall effect in graphene. Okay. So, the integer quantum Hall effect is given by the sigma x y, that is a Hall conductivity, is 4 n plus half E square over h. Okay. That is the formula. So, this is called as a half integer quantum Hall effect. So, this can be written as nu E square over h, okay, where nu has values which are minus 10, minus 6, minus 2, plus 2, 6, 10, etc. Okay. So, these are the quantization of the plateaus, and these plateaus are quantized with these nus. So, n is actually an integer, and these are positive and negative for the electron and holes, and these factor of 4 that you see here at the front, it takes into account the degeneracy, the pseudo spin degeneracy, which is A and B sublattices, as well as the degeneracy corresponding to the two valleys, that is the two Dirac points. Okay. So, your nu is equal to nothing but plus minus 4 n plus half, and even though we call it as an integer quantum Hall effect, it is actually a half integer quantum Hall effect, and because of this half factor that is there. If you note that your nu equal to minus 2 and nu equal to 2, okay. So, minus 2 and 2, so these two values, they correspond to empty and filled levels with eigenvalue E n equal to 0. That is the lowest Landau level. So, E n equal to 0. So, these for n equal to 0 Landau level, the n equal to 0 Landau level, for n equal to 0 Landau level, the valley degeneracy So, valley degeneracy is called as a isospin at times, and the sublattice is called as a pseudospin, is same as the sublattice degeneracy. And this is stated in a slightly different fashion when I said that the n equal to 0 Landau level actually receives contribution from only one sublattice and not from both. Okay. So, this Landau quantization for this non-relativistic dispersion that you have learnt earlier, it produces equidistant Landau levels, whereas here for the relativistic case there are non-equidistant. Okay. And as opposed to the usual degeneracies, or rather these usual n values which take usually positive numbers or including 0 for the harmonic oscillator, which we have seen again from the 2 DEG, here they are entitled to take, so these take negative values as well. Okay. So, these new values will dictate the values of n. So, n actually corresponds to the Landau level index, the same as the ones that we have derived, and nu is equal to plus minus this is the quantization of the plateaus. So, okay, these correspond to emptying and filling of the LL with n equal to 0, which means En equal to 0. Okay. So, this is 1 and this is 2. Okay. So, this is pretty much the quantum Hall effect in graphene, and it has been seen experimentally, and all these integers were confirmed from the plateaus. Let me show you the plot. So, this is the plot that one gets for the quantum Hall effect. So, these red plots are the Hall effect, and the green plots are the magnetoresistance plots, or rather magnetoconductance plots, and the plateaus are not at these black lines, but they are shifted by this half integer and seen at these blue lines. Okay. And they are not only at 0, but these blue lines also go beyond, or rather below 0, and these are like the only Hall effect in the left. This is the Hall effect, this red line is being shown, and you can clearly see the plateau structure, and the scale is not set by E square by h as we have seen earlier, it is set by 4 E square by h. Okay. And so, this is the quantum Hall effect in graphene, and if you want to see the difference between non-relativistic, so this is non-relativistic 2 DEG, and this is relativistic, that is graphene in chiral massless fermions, that is graphene, where you see the density of states is plotted as a function of energy, and you see that the density of state is bunched here and here. So, they are almost overlapping in this particular region, whereas there is a significant gap here in this energy. Okay. So, this distinguishes the quantum Hall effect seen in graphene and that in 2D electron gas.